Inside the nucleus of an atom, the strong nuclear force acts as the primary binding agent. It tethers protons and neutrons together with enough strength to maintain a dense, stable core. Opposing this is electromagnetism. Because protons all carry a positive charge, they naturally repel one another, exerting a constant pressure to drive the atomic structure apart. But between these two forces exists a third mechanic, a specific fault line in the architecture of the universe. This force does not seek to bind matter or repel it. Instead, it introduces inherent instability and mutation, forcing particles to change their physical identity. Physicists define this as the weak nuclear force. It is the sole fundamental interaction that governs radioactive decay. Unlike the other forces, the weak interaction is unique in its ability to physically hack a subatomic particle, rewriting its flavor to transform it into something else. This means the universe is not a collection of static objects. It is built with an internal flaw that causes matter to slowly, inevitably mutate over time. To see this mutation in action, we have to look past the surface of a neutron and into the foundational particles that construct it. These particles are called quarks. Their specific type, or identity, is classified as their flavor. A standard neutron is composed of one up quark and two down quarks. The weak force targets one of these down quarks, isolating it from its partners. When the weak force acts on a neutron, it forces a down quark to swap flavor, flipping into an up quark. The total charge shifts to positive, transmuting the neutron into a proton. As this mutation, called beta decay, completes, a high-velocity particle is violently ejected. Early measurements of these emitted particles showed a continuous range of energy values. This posed a direct contradiction to the law of conservation of energy, which required the energy released to be a single, well-defined amount. Beta decay is more than a structural collapse. It is an active subatomic transaction. To balance the quantum ledger, the process requires a physical messenger to carry away the energy difference. That messenger is a specialized particle ejected during the decay. This is the W boson, the heavy force carrier that mediates the weak nuclear force. In this transaction, the physics seem impossible. The ejected W boson is nearly 100 times heavier than the entire neutron that created it. This is the quantum equivalent of firing a bullet that weighs more than the gun itself. This chart shows the mass of a neutron compared to the massive scale of the W boson, which visually breaks the standard rules of conservation. Quantum mechanics allows this energy loan to exist only for an infinitesimal fraction of a second. The universe creates the heavy boson, but the debt must be paid back almost instantly. Because the boson cannot sustain its own extreme mass, it suffers immediate, catastrophic mechanical wear. The particle moves sluggishly under its own weight before it shatters into a cyan spark and a faint white ripple. The weak force relies on a messenger so inherently unstable, it must destroy itself to pay back the energy used to create it. When the W boson shatters, it reveals that the weak force does not follow the symmetrical rules governing the rest of physics. This is parity violation, the discovery that the universe possesses a structural bias, preferring left-handed chiral interactions over right-handed ones. Physicist Chien-Shung Wu provided the physical proof of this bias. She demonstrated that beta particles are not emitted randomly, but in a preferred direction. This experiment proved that the universe is not mirror symmetric. At its most fundamental level, the code of physics is asymmetric. The shattering of the boson leaves behind two remnants, a high-velocity electron and a mystery ripple. Every subatomic mutation triggered by the weak force leaves behind this highly specific exhaust signature. We can trace that signature to the faint, pulsing white ripple that survives the destruction of the boson. In 1930, Wolfgang Pauli proposed that an undetected particle was taking away the missing energy in the beta decay ledger. He postulated its existence years before it could be seen. Enrico Fermi later formalized this work, naming the particle the neutrino, or little neutral one. The neutrino is an almost massless, electrically neutral particle. It is the terminal exhaust of the weak nuclear force. Because it has no electric charge, it completely ignores the electromagnetic fields that armor normal atoms. This neutrality allows neutrinos to pass directly through solid matter as if it were empty space. It took decades of searching before the Cowan-Rines experiment finally detected this ghost in 1956. The missing energy from the subatomic mutation was never lost. It was converted into a non-interacting ghost exhausted into the cosmos. Scaling up from the interaction of single nucleons to the mechanics of the solar system reveals the true volume of this exhaust. The Sun is the primary driver of these interactions. Its massive nuclear fusion core is powered by continuous weak force decays. This continuous reaction turns the Sun into a massive neutrino engine. The engine pumps out a stream of subatomic ghost exhaust in every direction, saturating the solar system. To catch even a fraction of these particles, physicists build massive subterranean tanks lined with thousands of golden sensors. These detectors show that right now, 100 trillion solar neutrinos are passing through your body every single second. They travel at nearly the speed of light, treating the solid Earth and your own body as nothing more than a void. Right now, a blinding storm of white ripples blasts relentlessly through you, an invisible, ghostly current that never stops. The glitch at the heart of the atom creates a terminal exhaust that forever washes over us, a silent storm proving the fundamental instability of the universe.